All good.
Okay, so Paul Watson, contact details on the screen there if anybody wants to reach out to me after the event. I've been doing Informix now for just over 31 years. Formed on Init back in 1999, moved to the US 16 years ago, which was quite scary. Tend to specialize in enterprise replication, time series, and I've been doing UDRs for the last 20 years. So just sort of jump in and keep going. I'm trying to see if I can still see the chat. Should I be able to see the chat, Tom?
It's muted there. Chat is there. I will prompt you if anything comes up.
I'll shout out if I see something.
Okay, that's fine, because I'm not seeing it for some reason, but it could just be my end. Okay, so anyway, we'll jump into this. What we're going to touch on, an example of a few simple UDRs, how we go about registering UDRs, and I'm using the term there, software theft. Basically, how you can go onto Google, find a function that you might want to use inside the engine, and how you convert that standalone function into something that is a UDR. We'll mention a little bit of the internal magic that goes on behind the scenes when we're doing some of the UDR work. We'll touch on SQL and Cursors. We'll touch on Iterators, and then we'll obviously look at tracing and debug. I don't know whether this is a beginner's course, an advanced course, or an intermediate course, but we'll cross things as we go along. As I said, keep interrupting if there's any issues or any questions. Right, the myths. UDRs are a black art. They're not a black art. It's just C code. Okay, they're not difficult to write. It's just C code. They can be simple one-line statements, or they can be an entire application. They do crash the engine. That's a fact. It's just C code. If you write bad C code, like any other program, bad C code, bad program will crash a bad program. Unfortunately, if you write a bad CUDR, it will definitely 100% crash the engine. What it will not do is damage your data. You can protect yourself a little bit inside the engine by configuring how a UDR is run, but that protection is fairly limited. If you do something bad, it will take the engine out. I would also recommend that when you're writing CUDRs, unless it's very, very simple, you use some sort of covert or splint or some sort of static C code analysis to pick up any issues that might be there. The example code you'll be looking at will be, some of it will be real code, some of it will be pseudo code, some of it will just be a mismatch. So simple UDRs, there's 3 on the screen there for you. They just look after random numbers. You can't get much simpler than that. So there is no ability when these were written, and I still don't think there's any ability to do any random number generation with inside the engine. So these simple UDRs will just access the OS level, C library level functions, so you can bind them into your engine. As I said, you can't get simpler than that. Even an Oracle DBA can write those. CUDRs are always, with very, very few exceptions, faster than stored procedures. We've got an example there. It's a bit position UDR. It's similar to the stored procedure that's in sysmaster, the bit val. And we can see there that sort of unit testing, it's not quite 50% faster. It's about 40% faster. So like I said, CUDRs will always be faster. I have a pet hate. I hate the type Booleans, and I take every opportunity to tell people I hate Booleans. The problem with Booleans is they are a UDT, a user-defined type, which means when we're trying to do any comparisons with them, you might think just comparing a value to 0, a value to 1. We're not. We're actually comparing it via internal functions. If those internal functions aren't in memory at the time, we have to go and get them. If they're not in the UDT cache, we have to go and find them. We have to load them. We have to convert the Boolean into something that's comparable, and then we run the comparison. It's not as simple as a small int where you say, if I equals 0, if I equals 1. It's much more complex than that. So Booleans are definitely a slow data type, and if you can at all possible, I would definitely avoid them. So we're going to look at a real world example here. This is something that came out of a requirement, an Oracle DBA. They wanted to run a function inside the Informix database, and the function they wanted to use is Jarrow-Winkler distance. There's a URL on the bottom of the screen there that takes you out to Wikipedia so you can look up what it is. So basically, what we've got here is how we register that into the system. So we create the function, we tell it what we want to call it, we tell it what data types are going to be passed in, and what values are going to be coming back. In this case, obviously a float. We tell it it's going to handle nulls. By default, UDRs don't handle nulls. And by that, I mean, if you try and call a UDR with a null value, by default, we won't even get as far as the UDR. The higher level calling functions will block that, and we'll get an error. And I can't remember the error off the top of my head. We generally will want to run it in our own class. So when you do an onstat -g glow, we would see an on-init class there. Like I said before, they're supposed to protect you from doing dumb things that could take the engine out. My personal experience, I've never found that a great help. So like I said, the recommendation from IBM is always to run in your own class. User-based UDRs, I don't know if people are using things like time series or regular expression or any of the spatial stuff. When you first call that function, the engine will auto-register the function into the database for you. That logic is not available when you write your own C-UDR. So you have to register the code into the engine for you, into the database. So this Jarrow-Winkler distance thing, it's some sort of magic that came out in the 1980s, I believe. Someone came up with a way of doing some sort of statistical analysis on words. It's a built-in into Oracle. It takes two string values. It does some fairly simple math on it and comes back with a floating value about how close those two numbers are. It's a third-party piece of code. So if we want to bolt this into the engine, what we want to be able to do, or what we need to do, we need to look through the C code and make sure there's nothing nasty in there. And by nasty, I mean functions that are not allowed. We shouldn't be using anything like a malloc. We shouldn't be execing out to the OS. We shouldn't be forking. You can call them in a C-UDR, but they will crash your engine. So there's a list of functions that you're not allowed to use, and they're listed in the manual. The other thing to be wary of, if you're calling, we did this recently, we're doing some MQ integration into some third-party libraries. You've got to be a little bit careful. Those third-party libraries, we have to assume, or we have to know that they're thread safe, so we can actually use them within the engine. Professional, real, proper third-party tools like the MQ stuff we've been using, they're out there. They're recognized products, and we have no real issues about them not being thread safe. Turned out they were thread safe, so it wasn't a problem. But if you are going to the net and you downloading something, just be a little bit wary that what you're downloading is actually thread safe. if when you're examining your code, you see very, very tight loops, we'll want to put some yielding logic in there. So now if we're processing 1 million, we're looping through 1 million times and we're blocking out a CPU for no, tens or hundreds of milliseconds, we'll want to put a yield in there. So the engine will hold or yield that process back to the thread scheduler, and the engine will decide whether it's going to continue running it or it's going to give up the CPU to let it get on and do something else. So those are sort of general things you want to worry about that when you have stolen code off Google to try and add that functionality that you want. So how do we get this function actually into the engine? We can't just call that function directly. We have to rewrite either how it's called. So if we look back on the previous thing, we need to this area here, I'll change this slightly, give me a second. We would need to change this here to be Informix aware. So generally, the easiest way to do that is actually just write a simple wrapper that takes the parameters that are coming from the engine, which will typically, if they're strings, be lvarchar, and we have to convert them into whatever the function needs. In this case, we have to convert them into strings. So we will define the wrapper as a double precision function taking in 2 lvarchars. We also have a parameter there, which we'll touch on later, fparam pointer. We'll come back to that in a little bit. But what we're using it for here is to test whether the parameters we're passing in are nulls or not. Now, you can, when you register, as I said earlier, when you register function, by default, it won't handle nulls. The recommendation would always be to make sure in your code you put some sort of test like that. Because if somebody comes along at a later date and changes the registration to allow the function to handle nulls for whatever reason, they think they're being clever, they don't know what they're doing, or they just misunderstood something. If you call that function and you pass in nulls, when we get a bit later in the code, we're passing a null through. And as you know, obviously passing nulls around in C code is generally a bad idea. Again, you'll probably end up crashing the engine. So the recommendation is if you're throwing variables around, even if the UDR is not defined to handle nulls, there's probably a good idea just to put them in there anyway. Now, what we've done here in the middle of the code, we've got in the lighter green or the green code here, we've got 2 different ways of calling this function. We could just use the lvarchar data directly. This is this bit here. So what we can do, because the function is requesting a string, we could just tell it where in the lvarchar structure does that actual string start. So we will use the internal function published by IBM, migetVarData. That will return a pointer to where the data actually starts. We would need to know the length because the pointer when the data when stored in an lvarchar is not null terminated, so we need to know the real length. So we could do it that way by populating S1 and L1 with via the var data. But the problem is if the lvarchar data, that S1 and S2 pointer, might be changed by the function we're calling, then we can't do that. We're not allowed to write to that data directly, so we need to convert it into a string. So we would use this lvarchar to string function, and we'd convert the lvarchar to a string, find its length by normal string length, and then pass that down into the function. The my lvarchar to string will look after all the memory allocation for you. It will just give you back a null terminated string of the length of the lvarchar data itself. We will touch on these a little bit later. lvarchar to string in the engine is also available as in the client libraries, so CSDK libraries. They are not the same function. They have the same name, but under the covers they behave differently. We'll touch on that a little bit later on. When we come to return the data, we can't just return the value that come back from the Winkle function. We have to convert it to something we can pass further up the stack. So we have to allocate ourselves a pointer with the correct precision or correct size per routine. We'll touch on the per routine in a little while, and we will actually pass that pointer back up through the system. Now, in first case, that looks like we've got a potential memory leak because we've assigned memory inside a function and then we've exited without freeing that memory. The engine will look after that all for us as we pass stuff up through the stack. What it wouldn't do though is S1, the engine allocates memory for that. We would have to free that ourselves. Things like that, when you look up in the documentation, these functions, the documentation will tell you if you're responsible for freeing the memory that's allocated or not. Sometimes you are, sometimes you're not. Time series in particular, a lot of the time the engine will do some of the malloc and dealloc for you behind the covers, underneath the covers. So we've looked at how we'd steal code, how we get it in the system. Obviously now we need to make it, and I'm jumping back to the random numbers only because I can get a Makefile on one page. If you want to go to the URL there, you'd get all the code that you'd need to do this. It's a standard Makefile. There's nothing particularly clever in it, apart from the two lines that are highlighted in red. The include at the top will configure a lot of variables that you can use in your Makefile. It will allow you to know what the engine is, what OS you're running on, what the recommended flags are, etc., etc. The C flags there, you probably want to turn that up to the absolute maximum, warnings, pedantic, whatever you want to call it. So you want the code to be as robust as possible, and anything that the compiler can do to tell you you've done something dumb, you want to actually make sure you've done that. The other one in red there, we've got this variable mi_serve build. That tells the compiler that what we're doing, we're going to be building something that will live in the engine. That is something you definitely do not want to miss out. So we've got our Makefile, we've compiled the code, we've now got our .o or .bld down here. We've called it UDR BLD. We have to get this now registered into the system. And again, it's just a straightforward piece of SQL, create function, get random max. It returns an integer. We're going to run this in a class of RND, random number, and we have to tell it where it is. Now, we're using Informix dir extend. We don't have to do that. It could be anywhere. My general recommendation would be stick to Informix dir, because when we're compiling these things between different versions, depending on what you're doing, we could end up with some specifics that are engine unique. Time series is a particular good one on that. You really want to make sure you're tightly coupled to the engine. So I would recommend that you'd always create an extend directory and you put your own code underneath the version. Because we've got here, we told it we've got a class of RND. We need to tell the engine we've got a class of RND, and obviously we can put that in the onConfig and define it. We can start it up manually using the onMode command. There is one option on the class called no yield, and we'll touch on it a little bit later when we come into debug. By default, the the VP, when we're running the random function, by default, the engine will be allowed to interrupt that and say, look, you've been taking too much time. I'm going to stick you somewhere else while I go and see what else is needed. You can turn that off by setting no yield. So when the function is called, it will run to completion regardless of whether the engine wants it to or not. Maybe badly phrased, but the engine will not proactively interrupt the code. If you have something that's running in a very, very tight loop, running for a long time, by a long time, I would classify that anything over a millisecond, you will want to put a yield in there if you told it not to yield at the definition level, just to let it get back out of the engine. If you've got inside your function something that is logically a while true loop and you never get out of the true condition, that will run indefinitely and it'll take a CPU out for you because the engine will not be able to get in there and interrupt it. A couple of Makefile Gotchas. I said before, make sure some things are tightly coupled to the engine, and I keep coming back to time series because it's something I use a lot. We need to tell the compiler where the time series libraries are. So we have to add something to the C flags. So obviously Informix dir, whatever particular version we're running. We also have to set the library. If you notice there, we've got TSBE API, so it's a statically compiled library where BE means backend. We have to tell it where to find the library function. If you use the FE version, it will probably crash the engine because that's front-end only APIs. Also, remember to add the MI serve build to the GCC compilation line. The reason why making sure you've got the right libraries, as we mentioned earlier, the MI LVAR to string is syntactically the same, whether it's a front-end code or back-end code, but the implementation underneath the covers is different. You have the same in time series. You have certain functions that are syntactically the same, but they actually behave differently under the cover. Typically, it's all to do with memory allocation. If you were fortunate or unfortunate to ever attend any of my advanced SPL presentations, I always said there was no such thing as advanced SPL. And when we got looking at UDRs, I said that no, if you need to add this piece of magic, this MIF parameter to the end of your UDRs, and don't worry about it. It's just a bit of magic you don't need to worry about. Unfortunately, now once you get into writing C-UDRs, you do need to worry about this. So when the engine calls a UDR, it will automatically pass in this structure MIF param, which contains information about the state of the routine, the parameters that are being passed, the return types that are going to go back and forwards, whether things are nulls, whether we're working with an iterator, etc., etc. Like I said, it's added automatically to your code. So if you've got a function that's passing in two variables, it will automatically pass in the fparams structure, but you do not have to access it. So trying to explain this a little bit better. You've got two parameters being passed in. It will you optionally have in your code the need to add an fparams function. If there is nothing being passed in, you must, without exception, pass in an fparams thing. I'll show you on the next slide. So in this one here, we're calling UDR get rand max, and we must pass in that function. It's a requirement of the engine and how it works. If we were passing another parameter in there, so we were maybe doing a seed function, we would not have to pass that in. If we decide not to pass it in and we decide that we need it, there is an fparam get current, and that will get you the structure with inside the UDR. But 99.9% of the time, you don't want to do that. You just want to assume that you're getting the fparams being passed in. I said it gives you access to various structures. There's lots and lots, 30 or 40 accesses to the fparam structure. Feel free to go and look them all up online. The ones that we're generally interested in, we saw earlier, is the argument being passed in a null or not? And that is a null defined as an SQL null. An SQL null is not automatically the same as a C-based null. It tracks slightly different. It will also give us the state of the function, which we'll touch on a little bit later when we come to iterators in particular. But that function state allows you to track what you're doing at the UDR level across multiple calls. So if you imagine you've got a function, select my function bracket call one from table, within that, we can maintain state information across multiple rows returned from the select statement. So that is a common state to all iterations, all calls of that get routine. Memory. Obviously, we're going to be using memory. Never ever use the standard C calls. You must use the published APIs, and they are all MI underscore something to do with memory, alloc, zalloc, dalloc, etc., etc. They are all macros to the same underpinning C code, but you must use those to access memory. If you call normal malloc type functions, you will crash the engine. Where the system varies between front end and back end, we have this concept of memory duration. The default is per routine. So if we allocate memory and call a UDR, any memory allocated in that UDR, that function, is only visible inside that function. We can change the memory duration to per command, which is fairly typical, per session, which is very typical, and per system. Per statement execute and prep and transaction, I've never actually found a need to do that. The ones I tend to use are per command and per session and per system. The per session is very useful. If you imagine you've gone into your DB access or whatever and you've made a connection to the database, you can build up 50, 60, 100 SQL statements, and you will never have to do them again inside the system. If you put them into session memory, you could just go and grab them from the previous thing. An example of that would be some of the stuff that's used in some of the time series functions, where you do an initiator and you connect to the time series libraries, and after that, that area of memory is visible to the other time series functions that you're using until you disconnect and do a close down of that connection. Although I said you shouldn't use mmap because it's a system call, it's a C-level library, mmap can be very useful. Mmap will take a file from the file system, and rather than loading it through something like an fopen sort of logic and attach it into and read it into a buffer inside the UDR, mmap attaches it directly into the space that you're using. It's classified and it's in the notes that you shouldn't be able to use it. However, you can use an mmap to access that data. You've got to be very careful that how many CPU VPs you've got configured, and you have to be very careful about how you would access and update that. If you're using a no yield type single CPU VP, or sorry, single user VP, then you can use an mmap. So we've got the same sort of thing. You think about an external table, it attaches an SQL layer onto that onto the table and does the various mappings. You can mmap an unload file into your UDR and read that unload file without actually pulling it really into the buffers. You just got to be a little bit careful that you are only using that as a single threaded approach, and you're only opening one file at a time. If you want to use the per system memory, as the name suggests, it will allocate memory for the duration the engine is running, which is very useful when you want to share parameters across the system from multiple UDRs. The negative is it's per system. You got to be careful that you don't keep allocating yourself 100K of memory here or a meg of memory somewhere else, because you will not obviously blow through memory like you wouldn't believe. It obviously is released when you shut down the engine. It won't be there when you come back, but unless you explicitly release it within your UDR, it's there for the duration of the engine. So it's a fairly major potential memory leak. It's not a leak in the sense that it's bad C code. It's a leak in the fact it's bad memory management. Global and modular variables, you can't use them. Okay, they really can't use them. They don't exist in the context that you would know and love them in a C program. We've got an example here. It's very, very trivial code, and in this trivial code, you would probably be all right. So you need to think about this as more complex code. So we've got a modular variable there. My val, we've initialized it to my initial string. We've called a function myfunc1. We've just overwritten the value and we've returned it. And then we've got another function there, just returns the existing value. If we call this as a stored procedure, function 2 in any real world situation will probably crash the engine, because the value myval is not probably available inside the CPU VP you're currently running in. If you're running single CPU VP and you're running in a user class, a dedicated user class, and there's only one of them, it will probably work. But as soon as you move out into the real world, you will be crashing the engine, or you'll be getting some weirdness. So you've set my initial string to my really important data, and you've gone through, and function 2 is trying to process my really important data. Function 2 will probably have just random rubbish in there. So my really important data now is completely gone. You don't know what it is. So you can't use global and modular variables. So the problem now is, obviously, there's times we want to use them. You know, in stored procedures, for example, we have global variables. So we need to be able to use global variables. We need to be able to share things around the system. And the way we do that, we use something called named memory. Now, named memory is a chunk of memory we allocate out of the shared memory virtual segment. And it's, think of it as user memory. It's your personal memory to the system. And you can put whatever you want in there. You can have it whatever size you want, up to the engine limitations. You can change the validity and the scope of that memory. So that would allow you to store global variables. So you would create yourself an area of memory and allocate it to the session. And then anything you write into that global area of memory, or that named area of memory, is available to anybody else who's in that session. So you access this memory based on the duration and what you want to call it. You don't access it directly via the pointer. All you can do is say, what is my pointer to the memory I previously named? And you see at the bottom there, we've got pointer 1 equals some per system memory called my memory, and we've got pointer 2 looking at per session, and it's got the same name. The name is not unique, or it doesn't have to be unique. The name and duration, however, is unique. Pointer 1 will never ever equals pointer 2. If it does, I would suggest we want to do an assert failure and we're out of here. You are responsible for making sure that named memory is safe. So you can't have multiple people, multiple sessions. Sorry, sticking to system memory. We can't have multiple user sessions trying to write into that at the same time, because we will get potential overwrites in what's going on. So it is up to you as a UDR writer to make sure that you put the various mechanisms in place to make sure that can't happen. There are exposed functions that allow you to lock the memory, so you can set a flag on the memory, you can lock it, you can update it and do whatever you want, and somebody else comes along, they request the memory, and then you ask, is it locked? And if the answer is yes, it's up to you what you do. You can spin on the memory waiting for the lock to be released, or you can come back later. It's entirely up to you. Those spins, though, you're talking about microseconds here. So if you want to spin on the memory, you want to have a fairly tight, shallow loop. So you don't want to be spinning for 100,000, because you're basically spinning there for a second. And like I said, that's probably uninterruptible code. So you've locked part of the system for a second. So what would we want to put up into this system area? So, I mean, again, I keep coming back to the time series because I've done a lot of work with time series. So what we might want to do, we've got a time series based system that every session, every new connection has to build up some SQL strings, not fairly common, nothing particularly difficult there. It might run, say, a particular session might run to 50, 100 individual SQL statements that we need to run within inside that session. We don't need to generate those SQL strings every single time. We could create them once and put them out into system memory, and then when we want them, we can just go and look and say, right, okay, what is the SQL strings we need to use at the moment? And they'll be sat there ready, prepared for us. If the logic that give yourself an awful lot of time. And again, in my world, when I was doing some of this stuff before on the time series, we were taking out somewhere between 1 million and 2 million SQL statements a day just by keeping, or the build of 2 or 3 million SQL statements per day, just by keeping the string up in the system area. One of the other issues you get is if, again, I'll stick with time series. So I've written myself a UDR that needs to access a time series function. The only access I've got to that time series function is via the SQL layer. So we have a stored procedure, or a UDR called TS container create. The accessor to that is via the SQL layer. But I'm already in the UDR. Why do I need to go all the way back out to the SQL layer to actually access that function? Well, the slow way, I would do a mi-exec and I would use the SQL interface. But like I said, that is a significant overhead. So they have this concept, or this technology called Fastpath. And what it allows you to do is access functions that are not within your library, they're out in the engine somewhere, and you can run them directly as the C code. So if you look down here, it says that the key here is this line here. So it's basically allowing us to find out what TS container and its various parameters, where is that registered in the system, and how do we find that function descriptor? and we can go and find that, and then we can just execute it. So we're bypassing the SQL layer completely. Again, sticking with time series, there's a lot of time series functions that you might want, and depending on where you are in the code, you might want to use function A instead of function B. So you can build up a set of function descriptors and then use them like you would use a functional pointer in C, and just, I've got a variable whatever, and I'll just jump to within the functional pointer array, I'll jump to the relevant element, and I'll just execute the function that's there. So this Fastpath is an ability for you to bypass the SQL layer. And with time series in particular, that's a very good thing you want to do. There's certain things you can't do with Fastpath. You can't access iterator functions, and you can't call a stored procedure that has a resume word in it. So anything that is an iterate. So again, we're talking about here about using just an ability to bypass the SQL layer. So I'll just pause for a second. Has anybody got any questions?
We have about 8 minutes to go, Paul.
Oh, okay. We better get a bend on then. Okay.
We're kind of flexible on it, but yeah.
Okay. I said these set of slides were picked from a 3-day UDR course. So we're trying to compress 3 days worth of information into 45 minutes. So we'll keep going and we'll go from there. Okay, SQLs and cursors. If only we could use for each. Yeah, we go into 4GL and we do for each cursor into variable, and it is 2 lines, 3 lines. It's so easy to use. It's a piece of cake. Unfortunately, it doesn't exist in the UDR layer. What you now will start to appreciate is the heavy lifting that is actually done by the engine when you ask for something we consider really, really simple. Okay, so we need to write the heavy lifting code. Now, the further we get into a real cursor and for each loop, the heavier that lifting will do. But at the moment, we'll just look at some simple statements. So these here, if you just want to do a select, so you build up your select string, it's not returning anything, it's just doing something. Yeah, it could be a delete. This one's a select into a temporary table. We can just execute that directly. Okay, so we build our string. It's the logical equivalent of an execute immediate. And we can do the same with a function. We've got one down there. We're doing a time series loader initialization. We're passing in the parameters, and we're just executing it immediately. There's no rocket science in that. It's the same as what you do in an ESQL or 4GL program virtually. It gets a little bit trickier when we start into prepared statements. Okay, so here we're going to prepare something. So we're using a parameterized query for a parameterized statement, for example. So we've got this thing here. MySQL is building an SQL string based on whatever we pass in. It comes back with an SQL statement, and we just prepare it. Again, not an awful lot of heavy lifting there at all. It's just preparing a statement. But just because we prepared it doesn't mean we've executed. Like, again, in 4GL or ESQL, you would do the prepare, then you have to execute. So what we're looking for now is the equivalent of an SQL, exec SQL like we got on the line before. So we want to update something using a couple of variables. Luckily for us, or unluckily for us, there is a function to do this. Unluckily, it's quite a complex function. So we have built into the engine something called myExecPrepared statement. Just running down the comments on the green there, the light green. So we need to know the statement ID, and that would be the statement ID that is up here. So we have prepared statement LF, and that is actually a statement structure. So that would actually be a structure in its own right, containing whatever we need. So an MI statement structure, whatever we need for the engine to be able to understand what we want to do. We have to tell the engine, how do we want the data back? Do we want it back as text, or do we want it back as binary? We'll touch on that in a few minutes. What parameters are we passing? Sorry, how are we passing the parameters? Are we passing them as binary variables, or are we passing them as string variables? By string, I mean, even if the number is 2, we will pass it as a string. We're not passing it through as an integer 2. We have to tell it how many parameters are being passed. We have to tell it the values of the parameters, and we'll touch on the MI datum in a second. The length of the parameters. Are they null parameters? What are their data types? What will be coming back? Yeah, and what will the return types be? So if we just look at a fairly simple one, so what we've done here, this is fake code, obviously. We've assigned the values to be myString, null, and 22. We've told it how long they are. Notice they're not null terminate. We're not counting a null at the end. We said which of those are null. So 0, 1, and 0. And we're using the data types that are recognized by the engine. And there are functions in the engine that will give you those string variables back. Based on the call type of the SQL statement you've prepared, you can ask the engine, say, what is the column type for the third parameter in my statement, and it will come back and say lvarchar or date or integer or whatever it comes back with. Said we'd mention MI datum again. So an aside, MI datum is basically a void. It can hold anything that we want it to hold. As you can read on the screen there, it's basically a guaranteed safe structure. So the engine is completely portable across all architectures, the same as a void. It is defined as a void star. In our world, it'll be 8 bytes in length because most of us now are in 64 bits. The MI datum, depending on what the data type is, might hold the value. So if it's, if we come back up to here, we look at the values 22. So that's a string. So what it's going to hold in the second or final values array will be a pointer to a string containing 22. If we were using binary data, the 22 would be a binary, would be a value, an integer value, and values, a datum value would contain a position 3, it would contain the integer 22. So MI datum sometimes points to real data directly, sometimes it points as a reference to another part of the system. Again, coming back to my pet hate about my Booleans, so what you would have there for a Boolean, you would have a reference pointer out to a Boolean structure. If it was just a small int, it would just have 1 or 0 in there. So we've done now how we actually can run the SQL. So how do we get this to work? So we looked at how we can do an execute immediate using some variables, but how do we open a cursor, fetch the data back, and then obviously you have to close the cursor. This time we use a function called MI open prepared statement. It's very, very similar in its calling parameters to the execute prepare. It allows you to pass in whether it's a scrolling cursor or not, and whether it's a read or write cursor. Okay, so this is pseudocode, obviously. So we have to open the prepare statement. I haven't really expressed this strongly enough, probably. Every time you call an engine function, you want to test the return code. If it returns a null or an error and you don't trap it and you keep going with that null value, you will probably crash the engine. So you cannot over test the return code. So what we're going to do here, we have to open the statement that we prepared earlier, much like you would do in ESQL or 4GL if you're using an open logic rather than a for each logic. We have to fetch the statement. So we have to make sure that what we've asked for is actually valid. And then we run something called get result. And that get result will tell us whether that column, that select statement, or whatever we've done in the prepared statement is actually returning rows. So we can open a prepared statement that doesn't actually return any data. Think of that one we looked at before, the select into a temporary table. Yeah, that will not return any rows. So we always want to test that. Once we know we've got some rows coming through, we now have to step through every single row that we've got. And we're doing this at a row level. So if the select statement returns 10 rows, we'll go through this loop 10 times. We need to test to see if we got an error, because we always do. It's a select statement. We know it's a select statement, so it's not going to be a DDL and it's not going to be a DML. Now, it is up to you whether you decide that is an error condition or not. The more generic you make your SQL handler functions, the slower they will be, and that will take away some of the benefits of using C-based UDRs. We know this is a select statement, therefore we know this is going to be turning an MI row. So now we have a row of data. We know, because of the way we prepared the statement, how many columns we're expecting back. So we've got this variable here. I've just set it to numCol. So we've done select column 1 to 10 into, and we know we're going to be getting 10 columns coming back. So we step through those. We run a function called MI value on the row that we've got returned, and a length variable, a length pointer, sorry. If datum comes back as null, yeah, we've got to work out what we want to do with the null condition. If it comes back as non-null, we have to save the data. Now, we need to know the return type of what we need to save it into. If you're using a string return type, then you will need to allocate memory or have memory already allocated for that string. If you're returning data where the string value can change in length, you need to make sure that you don't accidentally overwrite the existing buffer. If you overwrite the existing buffer, at some point you will probably crash the engine. So you've got to make sure that you've allocated the right type of memory. If you're returning binary-based data, you have the same logic. You've got to make sure that you're putting a character into a character and an integer into an integer. There's multiple values on the MI value return. We know whether we're returning a normal value or it's a collection or a row or even a null value or an error. If you return, I tend to, if I'm using a normal value, I would normally just not worry about the null value. I would have logic in there to track that slightly differently. And obviously the bottom there, we got the default. If we don't have one of those 4 conditions, we've broken the engine, because those are the only 4 that are documented that can come back. So we're out of here, we broke it. Okay, iterators. When you're writing UDRs, there's 3 fundamental, there's a UDR, which is what we've been looking at. There's an iterator, which is a level of complexity up. And then we've got UDAs, user-defined aggregates, which are, we're not going to touch today, but they are a level harder. By default, as you know, if you run a select statement and it returns multiple rows when it's not expecting, we get a 284 error. SQL has not returned a single row. So we must obviously, at times, we want to do that. And the way we do that with as an iterator. We must define the function as an iterator function when we when we register. So basically, think a resume inside a stored procedure. That is an iterator function. That's what we're trying to do. And the iterator has 3 very distinct phases. When we set the iterator up, it gets called with 3 phases: an initialization phase, a return one row phase, and an end phase. So when it's called initially, we've got here my data. We're going to allocate ourselves some really complicated structure. We're going to do lots of setup stuff on whatever my data is. And then we're going to use this FP set func state. And that is what we mentioned very briefly earlier. This is the ability to store a state across multiple calls of the function. So I'm going to, on my set init, I'm going to create all the memory and all the cursors and everything I might need to do whatever my work is going to be. And I will set that up and I'll put it into the fparam function via the set function state. And now my data structure will be available across all of my calls to this routine. So I've done a select, I don't know, execute procedure 28, and 28 goes into a table and returns back 50 rows. So basically, because it's an iterator, the way it's defined, we will call this set init the first time, but everything we need to process those 50 rows are within that my data area. Note nothing is returned back to the client. The engine is doing this all internally, so it will call the set init, and it will, as if by magic later, go off and do the next bit. And basically, it's telling the engine we're good to go to the next phase. And the next phase is, right, so now I need to go and get my parameter from earlier. So I've got my parameter. We have to do something with that, and I don't know what the something would be. And then we process our data, and then we save the current state of our data, and we return our values back to the SQL layer. When we finished processing all our data, we tell the iterator process that we finished doing what we're doing. And that will automatically trigger the next phase, the set end phase. And here, your responsibility is to make sure you clean up what you've been doing, particularly memory. So depending on what you've done in my data or what that structure is, you might have to step through it, releasing all the memory. So you've got my data is a complex structure that's allocated a lot of statements, etc., etc. You cannot just free my data. You must go into the my data structure and release everything that's there. And then, because obviously, if you release my data, you can't get to the contents of my data. Engine will, there's a SAPI drain function that should be tidying up when you come out of the routine. Sometimes I have seen it fail. The problem is the SAPI drain, if you're using session-based memory, you've got a memory leak there because you're calling something back again and we've got memory allocated we don't want. The engine will try and clean it up eventually, but if that session is running for a long time, you've got a potential large memory leak. Any questions? Okay, well, nobody's said anything. Everyone's gone to sleep or whatever. Okay, replacing the UDR.
If you want to.
Yeah, I don't know. I can see the chat. That's a problem.
Yeah, I'm watching it. So if something goes in there, I'll let you know.
Okay, that's fine. As I said, I think everybody's asleep or bored. Okay. Yeah, could be. So replacing a UDR, by far the simplest way is just to bounce the engine, change the library and put it back again. If you just copy the library on top of the existing library, you'll crash the engine. Okay, think about it. It's like if you are just in the normal running engine and you copy a library, a different library, over the top of any of the libraries the engine's using, you'll crash the engine. The difficult way, you can unload a module. So we can unload part of the library. I've never found that particularly reliable. I've never found it particularly robust or safe. And I think, so I've tended to avoid it. I think you have to unload every exposed function within the library individually, but I wouldn't swear to that. Like I said, I've never found it particularly reliable. I tend to bounce the engine. Tracing. So a normal C program, if you want to know what's going on, you just scattered it with printfs or fprintfs or whatever you want to do, and it will just dump things out to the screen. That doesn't exist. Yeah, we can't do that. So the way we achieve that is a table called systrace class we'll touch in a second. And there is a macro, now a documented macro called dprintf. And dprintf, you can see on the screen there, allows you to write stuff out to a log file. So we've got something there, basically a string of what we're doing. The next number, the numeric value, is the debug level, for want of a better term. And then anything here, this part here is any valid complete SQL string. So we got %s main function, right? And it's going to put function into there. This one down here, it's going to, sorry, let's just clear all that a second. So this one here, this is a complete, that there is a complete valid C statement. So it's a valid printf statement, might be a better way of phrasing it. Dprintf is a macro. Depending on what you're asking it to dprintf, that macro will maybe expand slightly differently. So you want to be careful. If you're using it in a simple if or conditional loop, you might want to wrap it in braces so it doesn't expand out in such a way to destroy what you think your if then else logic is. Turn on tracing, we register function, this one on eTrace, and it calls two internal functions, trace file and trace file level. We register that, and then we give it an execution, granted execution. So now what we can do, we can call this function on eTrace, pass it in a file name, and pass it in a level, and everything here. So if we pass in level 20, it will dump everything to the screen that is 20 or lower. So we'd miss out 21 on that one, and it would write it out to whatever file we want. You want to be careful if you've got multiple traces running that you don't use the same file, because they'll just all be intermingled. So you want to probably trace it at a session level. You can do conditional tracing, which is very useful. So you can say, no, I'm doing conditional trace 30 here. So basically, if I'm tracing at level 30, instead of just continuing, what it's going to do, it's going to display and dump out in here purge detail. It's going to work out what various factors are, and it might, here it's giving me a purge factor. So it's working out the values that will maybe use later on. There also is a GLT printf that allows you to do GLS-based stuff. By default, trace is in American English. Very, very debugging here, very, very simple UDRs can be converted to a standalone program. So think of that, the random ones that we did earlier. Anything meaningful probably cannot be converted to a standalone program. The reasons being, the main reasons being, the functions in the client libraries are not the same as the functions in the backend libraries, particularly time series. And we mentioned earlier that MI varchar to string. MI varchar to string can allocate memory at different memory durations when it's running in the server. it can't do that at the back end. So the functionality is not the same. So simple UDRs you can convert to a standalone. Anything meaningful you can't. So how do we debug those? AF trace is always your friend. A little bit of experience, you can normally look at the stack trace, and it will tell you, well, it'll definitely tell you what function it's gone over, and normally you have a light bulb moment that it's, because I've overrun this buffer, or this variable's not a set, or something like that. And depending on what is called between your function and the AF function, it'll point you in the right direction. IO errors at a GNU level, GCC level, and nearly always just some sort of buffer overrun. Scattered debug code throughout your UDR. This is not standard C activity. So using a hash defined debug, and I pass that in from the compile line, and it will give me more information. Always have a dprintf call before you exit your UDR. So you've done all your logic, you've closed everything down, you're just at the return back to the calling function, put a dprintf there saying something like out of here or closing UDR. The reason you want to do that is when you look at the trace file, when you've got it active, if you see that, you know the problem is after you've left your code. Now, the problem might still be in your code, but you know you're being passed up to the executor functions that run the UDRs. I mentioned earlier, there's a function sappy drain. There was a bug in sappy drain under 12. If you released all your memory, so you freed all your memory, when it was passed back up to sappy drain would then try and free a null pointer, and that would crash the engine. That was a bug in the engine, but to trace that down, we could only trace that down because we knew what had happened. We'd exited the UDR. And then obviously, if you're using that hash debug, you compile that into your as part of the compilation. As I said, you can't convert into standalone programs, so it takes a little bit of effort to debug them. The first one is set a VP class of whatever you want to call it, set it to 1. So you now know, and no yield probably. You now can look, compiler with GDB3, so you've got the symbol information in there. On stat-g glow, find the PID of the VP class you've created. So here we've got my class. So on stat-g glow, find out what my class PID is. GDP -p my class. And now you are debugging the live code. You've got the symbol information in there. You can use all your standard GDB functionalities. 99.9% of the time, any crashes in your UDR will be your fault. You have done something dumb. Memory, buffer overruns, nulls. The engine. I've worked with people, their go-to starting position was the engine's broken. Your go-to starting position has to be, I've done something stupid. As an aside there, working on something else recently, just running GDB on init -v is fascinating. Yeah, you'll find out so much about how the engine starts up and what it does, etc., etc. Oops, sorry, go back one. Couple of things to always include. I like to put a version string inside my and expose that as a function, so I can do select or execute any version, and it'll come back and tell me what version I'm running, because just I know then that I'm running 1.2. Whatever you, however you want to do it. Mentioned earlier, always put a dprintf before you exit your UDR. Always, if you've got your functions in your libraries that are exposed, prefix them as something that's unique to you. We did a port back in the day when regex was, before it was built into the engine, the code, regex, that functionalities, those UDRs, they have the same name as the standard Linux regular expression C-based libraries. So depending on what your load library path was set to, your engine would or would not crash. So by going into this, the fix we did, we went into the reg expression code, the open source, and we just basically changed the names of the functions. The problem went away. If you can operate in binary data, Informix binary data, it is significantly faster. For an example, we're doing some work with a 1,000-line unload file, which we're loading into the system. We're processing it, doing various bits and pieces on it, and throwing data out at the end of the day. By loading that file, that ASCII data, into memory, then scanning the ASCII data, converting it into Informix binary format, and then processing the binary formatted data, we reduced the runtime by 40%, even allowing for the overhead of converting that data into the right type. If you can operate in a binary environment, stay in a binary environment. And that's all I've got.
Oh, thank
Any
you so much,
questions?
Paul. I